And Steven's area is random fields, and especially he is interested in random walk and different geometric aspects of random fields. And during this really very short period after his graduation, he published, as I can see, a lot of papers, interesting papers. And today he is presenting some of his results. Yeah, so recently Steven joined back Melbourne Uni as DECRA. If you are not from Australia, probably you don't know DECRA is really very prestigious award and scholarship of Australian Research Council for young researchers. And Steven started his DECRA, I believe, from September, but he's still abroad, so he probably will be moving to Melbourne very shortly. Okay, Steven, the floor is yours.
No,
okay,
no,
so
no, I just want to welcome Steven here. Sorry, that's my point. Because we haven't properly welcomed him in Melbourne yet. It was just announced around the school that he has joined us from the 1st September, and this is the first chance for us to see him live on Zoom, but still live. So welcome to Melbourne, Steven.
Thank you, Kostya. Thank you, Andre. Yeah, so it's very nice to have this opportunity to talk in the seminar and to talk in front of new colleagues, even in less than ideal circumstances. So I won't really be presenting any kind of overview of my work. I'll be talking about very recent work, actually. It's not even on arXiv yet. We hope to have it on arXiv very soon. And I'll be talking about joint work with Alejandro Rivera and Hugo Vanneuville. And what we try and do in this work is understand the phase transition for a certain class of percolation models, which are built out of Gaussian fields. But what's important and what's significant about this class is that they don't satisfy necessarily this key property of positive associations. If you know some percolation theory, then you'll know that this FKG inequality, this property of positive associations, is really crucial to most of the theory. And if you don't have it, then a lot of your techniques break down. So we were interested in trying to extend the techniques to this situation where you don't have this key property. Okay, so the basic object under consideration is a smooth planar Gaussian field. So just so we're all on the same page, what this means is that it's a random smooth function on the plane such that its distribution at any finite number of points is a jointly Gaussian vector. And Gaussian fields are interesting in part because they have nice mathematical structure that makes them tractable models of spatial noise. But they also appear in applications. So for instance, you can model, say, the surface of the ocean, or the cosmic microwave background radiation, or any kind of random energy landscape using a Gaussian field. These appear throughout physics, really. So one of the nice things about Gaussian fields is if you assume that they're centered, meaning that their mean value is 0 at every point, and you assume that they're stationary, meaning that their law is translation invariant, there's no marked origin, everything is completely symmetric under translations, then everything is uniquely defined by its covariance kernel. A single function tells you everything, completely prescribes the field, this two-point correlation function. But nevertheless, within this class, you still have a wide variety of possible behaviors. In fact, any positive definite function will give you, covariance function will give you a Gaussian field, and they can have vastly different properties, as we'll kind of touch on in the talk. Okay, so the question we consider is the level set percolation problem associated to this field. That is, if you fix some level, L, and you consider all the points on the plane that either attain the level, that's the level set, or all the points that lie below the level, that's the excursion set, then we're interested in understanding for which levels these things have bounded connected components, or whether there's a possibility that they have an unbounded connected component. Could there be infinite excursion sets? Just to give you an idea of why that's an important question and why it was considered already in the physics literature 50 years ago, is if the Gaussian field models some sort of random energy landscape that is confining particles. So you have a particle sitting on the plane and it's being confined, it's sitting in the valleys of your random energy, your energy landscape, then whether or not you have unbounded excursion sets of your whether or not you have unbounded excursion sets tells you for which levels your particles have the possibility of escaping their valleys, or whether or not they're going to be confined, they're localized to certain regions of space. Okay, so what can we say about this problem? Well, there's an immediate observation to make, is that you have monotonicity. So therefore, there exists a critical level at which you have the possibility of unbounded excursion sets. So how to understand this is you can imagine your random energy landscape, and you can imagine flooding it with water starting from the bottom. So you raise the water level, you have kind of rising sea levels, and at the start you have all lakes, all your valleys are flooded into isolated lakes, but after some critical level, then you think that all your lakes will merge together into an ocean. And so, yeah, straight from the fact you have monotonicity, that allows you to define this critical level, but it doesn't tell you anything about it. It doesn't even rule out the possibility that it's infinity, which means that there is no finite level at which you have unbounded excursion sets. And it doesn't rule out the possibility that it's minus infinity, which means that you always have unbounded excursion sets at every level. Okay, but there's a very important insight to make, an immediate insight to make in the structure of the model, which is that you have a single level, that is the zero level, has the special property of self-duality. So what that means is that at the zero level, the set of points that lie below that level and the set of points that lie above that level are equal in law. And this comes from the symmetry of the multivariate Gaussian random variable. And this is some concept of self-duality. And by analogy with all the other statistical physics models on the plane, it's completely natural at that point to predict that the critical level is the same as the self-dual level is zero. So somehow this symmetry at zero is going to suggest that the critical level is zero. Okay, and that's what the physicists conjectured all the way back in the 70s. So what the physicists said is that if your Gaussian field has some very mild properties, so you certainly need ergodicity, otherwise it's false, and perhaps some other mild conditions, then the critical level is zero. Of course, these are physics literature. They're not really clear what they mean by mild conditions. And more than that, they don't restrict themselves to Gaussian fields. So the physicists claim this is true basically for any stationary, smooth, random field. But certainly it's false in that level of generality. It's not the case that self-duality immediately gives you the critical level being zero. You need some structure, because it's easy to build counterexamples where this doesn't happen. So clearly the structure of the Gaussian field is going to play some role in allowing you to prove such a conjecture. Let me be a little bit more precise about what the conjecture entails, because it has two parts to it. It has a subcritical part and a supercritical part. So what it says is that subcritically, if the level is less than zero, then your connected components are bounded. But it also suggests that at the zero level, you should also have bounded connected components. Because if you see in the definition of the critical level, it leaves open what happens at the critical level. Because of how it's defined via this infimum of levels at which you have unbounded connected components, at the critical level, you could have bounded components or you could have unbounded components. But the conjecture suggests they should be bounded. And that's actually equivalent to saying that all of your level sets are bounded at every level. And on the other hand, if you go above zero, then you should have unbounded excursion sets below that level. And moreover, they should be unique. There should only be one unbounded ocean. You shouldn't have multiple oceans. Okay, so that's the conjecture. And let's just place this into context of statistical physics more broadly, because there are some probably more familiar to you, models that are more familiar to you, it's useful to compare to. So let's start with maybe the most famous model of this class, that is simple Bernoulli percolation on the hexagonal lattice, say. You could also do this on the square lattice, but the picture is nicer on the hexagonal lattice. So here, just to be clear, we start with a hexagonal lattice and we color every point black or white independently with some probability, P. What Keston famously proved in the 80s is that P equals a half is the critical point of this model. And at first glance, it seems kind of obvious why P equals half is the critical point. And it's for the same reason I explained, because you have self-duality at that point. At the point half, the law of the black and the law of the whites are equal. And you'd think this is some natural property to have at criticality. But let me point out that it took a long time for Keston to prove this. This problem was raised already in the 50s, and it took, for 30 years, this was the big open problem in percolation theory. until Kasteleyn famously proved it in the 80s. So it's not obvious how you get criticality from self-duality. Okay, let's go up in complexity. So more recently, people have been trying to do the same thing for more complicated percolation models. So in the model that's called Poisson-Voronoi percolation, you no longer have a fixed lattice. You generate the lattice randomly. So you take a set of Poisson points on the plane, a Poisson point process on the plane, and you use that to generate the Voronoi cells associated to those points. So that means that you for every point on the plane, you look at which Poisson point is closest, and you partition the space into these cells that collect up all the points that lie closest to one of your Poisson points. And that's this cellular structure. It's a randomized version of some lattice. And then on top of that, you color your cells either black or white with probability P independently. And so what Bolobash and Riordan proved about 15 years ago is that P equals 1/2 is also the critical point for this dependent percolation model. And it's also the self-dual point. Okay, and finally, a connection in a different direction is the Ising model. So this is a different model, class of model, because it's exactly solvable. So this was understood already in the 1940s. But once again, the critical point is also associated to some self-duality. So here the self-duality is a little bit different. I want to explain it, but it goes under the name Kramers-Vannier duality. And so, yeah, it has the analogous behavior that the critical point is the self-dual point. Okay, so let me return to the setting of Gaussian fields and introduce the most important, the motivating example for our work, really, which is this random plane wave. There's a special case of the Gaussian fields we consider. So the random plane wave, well, it's a stationary planar Gaussian field, which means that I just need to tell you its covariance function to define it. And its covariance function is the zeroth Bessel function applied in the radial direction. So it's an isotropic field. It's rotationally symmetric, but its correlations-decay like the Bessel function. It doesn't really matter what the Bessel function is for the purposes of this talk, but let me just identify its asymptotics for you, because this is important. So it decays quite slowly. It decays like 1/square root distance. So that's a relatively slow decay. And it also oscillates. So it oscillates like a sinusoidal wave with up to some error term. So there are regions at which it's positively correlated, regions at which it's negatively correlated, etc. So why is this thing important? So it's very hard to see what's going on if you just look at the Bessel function. So it makes sense to go into the Fourier domain. If you Fourier transform this planar covariance function, you get something very nice. It's just the Lebesgue measure on the unit circle. The Fourier transform of this function is a measure. It's just the uniform measure on the unit circle. So a singular measure on the plane, but it's Lebesgue on the unit circle. So what that means is that inside your Gaussian field, you have only a single energy. On the spectral side, your measure is concentrated on a single energy level. And so you can consider the random plane wave is really the Gaussian object in the space of functions that satisfy the wave equation with fixed energy. So maybe it's better to think of it as some random superposition of sine waves in uniformly chosen direction and with uniformly chosen phase shifts, but all of which have fixed energy. So that means that this object arises naturally whenever you have some very chaotic system on the plane, but when there's an associated energy level, a single energy level associated to it. So for instance, a good example of that are eigenfunctions of the Laplacian on chaotic domains. So here, the setting is deterministic now. So consider this chaotic domain, this stadium. So yeah, I don't want to get into its dynamical theory or anything, but let's just talk about this on a very high level of rigor. So let's consider this stadium domain. It consists of a rectangle with half disks placed on either end. So this is an example of a chaotic domain. And what that means is, or one way to think about that is, it means if you take an eigenfunction of the Laplacian on this domain with Dirichlet boundary conditions, and you look somewhere in the center of the domain, you'll see something very chaotic. So that's what the picture on the left is. This is a deterministic eigenfunction of the Laplacian. If you like, you can imagine you have a drum shaped like this, and you hit the drum with some high frequency, then the drum will somehow approximate this picture on the left. So here the black and the whites are the excursion sets, the positive and negative, the places on the plane where the eigenfunction is positive and negative. So this is a heat map, I guess, of the eigenfunction. Okay, and on the right, you have a realization of this random plane wave. And you can see that it was already observed by Berry in the 70s, the physicist Michael Berry, that these look like they have very similar statistical properties. And so you would think that the random plane wave is some model for high energy eigenfunctions on chaotic domains. And there is a way to make this conjecture precise, but yeah, I won't go into that. Okay, so that's the motivation for why the random plane wave is interesting. And here we have the conjecture. Let's just apply it to this field. So this is a special case of the conjecture in the 70s, but more recently it was made by Sodin. And it says that the random plane wave has critical level 0. So if I go a little bit below criticality, if I go a little bit below 0, all of my excursion sets are bounded. If I go a little bit above 0, then I should start to have unbounded excursion sets. And notice that I've coupled these two pictures. It's the same realization of the field at different levels. So you have exactly the same excursion sets. It's just that since I've increased the level, I've added in a little bit of black, and the little bit of black I've added in has suddenly merged all my connected components together to give me some giant connected component. So this is what we mean by the phase transition occurring at level 0. Okay, so yeah, that's the context of the problem. Hopefully I've explained the conjecture and why it's important. And now I want to talk about what was known about this conjecture previously before our work. Okay, so there's been quite a lot of work on this conjecture, starting in the sort of 80s and then kind of tailing off a little bit. And then in the last 5 years, there's been a lot of progress built on the progress made in parallel on other percolation models. And what the state of the art is at the moment is that the conjecture has been completely proven for a class of Gaussian fields that satisfy 2 important structural assumptions. Let me explain what those are. So the first important assumption is what I said right at the start, this assumption of positive associations. So what that means is that increasing events are positively correlated. So an event is said to be increasing if, whenever it holds for the field, if you increase the field by something positive, then it still holds for the field. So for instance, the event that a unit disk has the function lying above the level 2 all on the unit disk is an example of an increasing event. Or in a more percolation context, the event that there's a excursion set that crosses a square is an increasing event. And positive associations tells you that all increasing events are positively correlated. And for Gaussian fields, we have a nice criteria which tells us when this is true, due to Pitt in the 80s. And Pitt's result was that it's true whenever you have pointwise positive correlations. Okay, but these are not the same thing in general. So it's clear that to have positive associations, it's necessary to have pointwise positive correlations. If you just look at events that are defined with respect to 2 points, that's clearly necessary. It's not clear at all why it should be sufficient to have 2-point positive correlations. But for Gaussian fields, it is. It's one of the nice structural properties of Gaussian fields that positive associations is equivalent to positive correlations. That's not true in general. Good, okay. And let me try and explain in one slide why it's so important to classical percolation theory. In classical percolation theory, it goes under the name the Harris inequality or the Fortuin-Kasteleyn-Ginibre inequality. But basically what it allows you to do, at least for planar percolation, is to make these so-called gluing constructions. So let me try and explain this. So if you want to say that you have a percolation cluster that crosses some large rectangle, so for us, this will be an excursion set that crosses this large rectangle, then you can say the probability of crossing a long rectangle is at least the probability of crossing a small rectangle cubed. Why? Because I can overlay 3 crossings of small rectangles in a way that forces a crossing of a large rectangle. So if all the small crossings occur, that forces, they link topologically, they link forces a crossing of a large rectangle. Then I use FKG to give me this lower bound. So it allows me to glue different crossings together and whilst maintaining lower bounds on the construction. And this is really crucial to most of the theory of planar percolation. Okay, that's the first property that is needed for this result. The second property is one of rapid decay of correlations. So we can call this short range correlations. And even though there may be different ways to make that precise, what turns out to be important is the integrability of the covariance kernel. So as soon as the covariance kernel lies in L1, you fall into this class of short range correlations. And basically it allows you to compare your field to one that has finite range correlations. So it allows you to really compare to Bernoulli percolation. And in particular, you can prove that if your covariance kernel decays sufficiently rapidly to be in L1, you get decoupling of crossing events on far away domains. If you take two, say, squares on scale R, separate them by a distance R, then whether or not you have a crossing of these squares will be almost independent, at least asymptotically as R goes to infinity. So you can see it allows you to do decoupling, which clearly is important if you want to make some analogy to IID percolation, Vanneuville percolation. Okay, so let me be a bit more precise about previous results. So actually the first result for which this was proved was only in 2016. And that was by Rodriguez, and he was interested in the case of the massive Gaussian free field on the square lattice. So here the setting's a little bit different. It's not in the continuum, it's on a discrete structure. And it's not a smooth Gaussian field, it's a Gaussian field on Z2. So let me not explain what the massive Gaussian free field is. But anyway, it's enough to say that this field does have these two properties, positive associations and short range correlations, but it also has a lot of extra structure. And Rodriguez used this extra structure to prove this result. So more recently, say over the last 3 or 4 years, in joint work with Hugo and Alejandro, and also Christophe Garbin was involved, it's been proven that zero level is critical more or less completely if you have these two assumptions. And how all these people did this is they make a comparison to Bernoulli percolation. That's really the strategy. Okay, but what happens if you don't have these two properties? Because let me remark that the random plane wave has neither of these properties. It's neither positively associated, nor does its correlations, nor is its covariance in L1. So it doesn't have either of these properties. So none of these results say anything about the random plane wave. What happens if you just have one of them? Well, then you have at least some partial results. Let me mention these. So if you just have positive associations, so if you just know that your covariance is positively correlated, then at least you can say that the critical level is positive. It's non-negative. And this goes back to some work in the 90s or 80s even. So this is a partial result under just positive associations. If you just have short range correlations, then even less is known, but at least you can say that the critical level is not infinite. At least there's a non-trivial phase transition. And this is due to Molchanov and Stepanov in the 80s. And then much more recently, Vincent Bafara and Damien Guy extended the results on positive associations to a certain perturbative regime. So they said that, well, this work of Alexander, etc., it does still work if you perturb to allow for a little bit of negative correlations. But yeah, it's really perturbative and it doesn't say anything about the random plane wave. Yeah, as I mentioned, the random plane wave satisfies neither of these properties. So none of the previous work said anything about the random plane wave. Yeah, so it was not even known that the critical level was finite. What could have happened is that every level is supercritical or every level is subcritical. You never have excursion sets that are unbounded, or you always have unbounded excursion sets. Even those weren't ruled out. Okay, so that leads me on to our result. So what we prove in our result is we basically settle this whole conjecture, at least, well, for a very wide class of Gaussian fields. And in particular, we don't need either positive associations, nor do we need short range correlations. So what's nice about this result is that it applies to this very special case of the random plane wave, which doesn't have these properties. Okay, so let me try and be a bit more precise about the wide class we consider. It's not every Gaussian field. We do need some assumptions, but I want to advertise that they're quite weak. But let me be precise about what they are. So what assumptions we need? Well, everything I want to talk about is about smooth Gaussian fields. Because if you want to talk about level sets, you at least need some smoothness. Otherwise, you start to have fractal structure, which you don't want to. That's a separate question. It's interesting, but we don't want to consider fractal structure. So let me just say that the field should be at least C3 smooth. That's going to be enough for us. You want some concept of non-degeneracy, and it turns out to be enough to be non-degenerate at 2 points, as long as you have your derivatives as well. And you need some covariance decay, but you don't need anything really strong. So let me just say here, you just need any decay to 0, at least to get partial results. But let me point out that this already implies ergodicity. So I mentioned right at the start that you should have ergodicity. Clearly it's false if you don't have ergodicity, but this is a little bit stronger than ergodicity. Okay, so you want correlations to decay at infinity. We also need some symmetry in the field. So symmetry is very important in Bernoulli percolation as well, like symmetry, using symmetries of the lattice. So we want to recover some symmetry. There are two different concepts of symmetry that turn out to be useful. The first is what you can think of as D4 symmetry, the symmetry of a square. So this is where you assume that the field is symmetric under both reflections in the axes and also rotations by pi/2. So here you're saying that the field has square lattice symmetry. But sometimes you need extra symmetry. So isotropy implies D4 symmetry, but it means something more. It means you have full rotational invariance. Okay, let me state our results precisely. So suppose, first of all, that the field satisfies just these three assumptions, these extremely mild assumptions before. Then, and suppose the field is D4 symmetric, then already that's enough to tell us that the critical level is non-negative. And that's already enough to tell us that all the level lines are bounded, except perhaps at the 0 level. So all the non-zero level lines have only bounded connected components. It's the first part of the result. Then if you suppose in addition that you have isotropy, and you suppose in addition that you have covariance decay that's a little bit quantitative. So let me point out that this is quantitative covariance decay, but it's incredibly weak. We're just saying that it's decaying like 1 over log to some power. So this is barely decaying at all, but it's a little bit stronger than saying you have qualitative decay. Then we can prove the conjecture that the 0 level is critical. So in particular, the random plane wave very clearly satisfies all these assumptions, and so it's true for the random plane wave. Okay. Yeah, maybe I'll pause for questions at this point if there are any.
I have a question.
Yes.
Can you hear me?
Yes.
Yeah. So all your previous assumptions, they are on probabilities or covariance function. And now you assume something about random fields, about trajectories of random fields. So these are different types of assumptions. And I somehow believe maybe assumption 1 would be rather easy. Smoothness can be expressed somehow in properties of covariance function. But how about assumption 2? Yeah. So because when you put assumptions and you tell that my random function has trajectories of such type, I think it's really very strong. Usually you ask about properties of covariance functions, probabilities, finite dimensional distributions, but not about properties of trajectories.
Okay, yeah, so it's a good question. So let me just say, okay, first of all, in terms of symmetry, this is completely equivalent to the covariance of kernel having these symmetries. So this is expressible completely in the same way in terms of the covariance function. So you're correct about smoothness. It's very easy to get a sufficient condition in terms of the covariance kernel. So we could say the covariance kernel is C8 smooth is going to be enough to imply the field is almost surely C3 smooth. This is Kolmogorov theorem. Yeah, you're correct. Non-degeneracy a little bit less easy to see how the covariance kernel should imply this, but there are sufficient conditions. So it's, for instance, sufficient that the spectral measure has a density that has a open set in it. That's sufficient, but the random plane wave doesn't satisfy that. So another sufficient condition is that the spectral measure contains a circle in its support. So if the spectral measure has, or any elliptic curve in its support, or any arc of a circle is already enough, then you can prove this non-degeneracy. So you can write down sufficient conditions, and you can check that the random plane wave satisfies this non-degeneracy. But for us, it's kind of more natural to express it this way because it highlights exactly what we need. But yeah, these are all expressible, at least in a sufficient conditions in terms of the covariance.
No, but sorry, maybe I'm asking too many questions, but it might happen then that your class of random fields, even if you consider the previous case is not covering all cases from the previous assumption, because you assume additional things about covariance, function, and other things. Yeah, it might be that, for example, your class covers a new class of random fields and partially class which was considered before, but not all cases from the previous class because of these additional assumptions.
Yeah, so I was being a little bit vague when I was reporting on previous results. For instance, these results. So these mild extra conditions are exactly what I've talked about later. So as well as needing this strong assumptions, you did need these mild conditions. So for instance, you did need smoothness, you did need non-degeneracy, you did need symmetry. So yeah, our result is a strict generalization of all of these results, actually. On the other hand, okay, maybe it's not a strict generalization of these results. So these work under slightly, different conditions. Yes, it's not a strict generalization of some of these results. That's true. Because for instance, this result just needs positive associations. It doesn't need any covariance decay. Actually, no, I think it needs ergodicity. It needs ergodicity. Yeah.
Thank you.
Yeah. Okay, but so I can just advertise, well, the random plane wave is a motivating example. It does satisfy our conditions. It doesn't satisfy previous known results. So at least that much is certainly the case. Okay, thanks for the question. Good. So let me say that even though we settle this conjecture about the zero level being critical, there are still many open questions, very interesting questions about behavior of, say, the random plane wave that are open and I want to advertise. Okay, so let me first say, well, what's kind of interesting about our work is it applies without this property of positive associations. That's maybe the most important feature of it, because there are many other models in percolation statistical physics that don't have FKG, don't have positive associations. For instance, if you take an Ising model with it's anti-ferromagnetic, which where the coupling constants are negative as well as positive, and this does not have FKG. So this is an example. You have certain regimes of loop models or random cluster models. You have if you take Voronoi models or Boolean models on point processes that are not Poisson, you don't necessarily have FKG. And there are other examples. And in general, these are really poorly understood models. And to our knowledge, our results are actually the first rigorous computation of a critical point for a model that doesn't have FKG. At least one that's not in a perturbative regime, or one that's an integrable model, say. So there is this prospect that our techniques could be extended to prove a lot of new results on other classes of models, but it's not immediate because we do use Gaussianity. And I hope to have time to explain why Gaussianity is important to what we do. Okay, so the second is, really the most important question now is what happens at criticality. So we've identified that the zero level is critical, but we don't say anything about the critical point. So we don't say that zero level lines are bounded. So this is still open, and this is a very challenging question. Let me just compare it to Bernoulli percolation. So on the plane, it's completely settled already by Harris in the 60s. But if you go to higher dimensions, it's still not known what happens at criticality for Bernoulli percolation. So for instance, on the cubic lattice in dimension 3, we know there's a phase transition, but we don't know whether or not there's bounded connected components at criticality. This is sometimes called the continuity of the phase transition. This is the most important open question in percolation theory at the moment, and has been for 30 years, 40 years. And so the analogous question for us is also open, and we expect it to be quite hard. If you have FKG, then you know this. If you have positive associations, you do know that there are no unbounded level lines at 0. But without FKG, we don't know how to do this, except for a perturbative regime. So let me advertise the result of Bafara-Gaye. They managed to prove this without positive associations, but only in a perturbative regime. Okay, so the third question that's interesting is, what are the quantitative properties of the subcritical and supercritical phases? So in particular, what you would expect by comparing to Bernoulli percolation is that if you go less than 0, not only are your excursion sets finite, bounded, but they're very small. So they should have logarithmic size, they should decay exponentially in their radius. This is known as the sharpness of the phase transition, that you, when you lose infinite components, you lose them in a major way, that they're all suddenly very small. But we can only prove this if we have short range correlations. So for the random plane wave, we can't prove this. And in general, our techniques give us some qualitative decay that depends on the decay of the covariance. Translated to the random plane wave, all it tells us is that it decays like e to the minus square root log. So this is very far from being exponential decay. And yeah, we're very interested in trying to bridge this gap, but again, it seems quite challenging to prove exponential decay. And maybe it's false. We don't know for sure if it's true. And finally, a connection to conformal invariant scaling limits. So it's been just like the boundaries of the percolation clusters are conjectured, in some cases known to converge to these conformal invariant scaling limits. It's also been conjectured by physicists Bogomolny and Schmidt, and further back by Vanneuville, that the random plane wave lies in the Bernoulli percolation universality class. So that means that the 0 level lines, the critical level lines, should converge to this conformal loop ensemble with parameter 6. Yeah, I won't say too much about this, but this is a big question in physics, and it's supported by numerical evidence, but we really don't have any idea how you would get the conformal invariance to appear. So this is, yeah, a big challenge for the future. And there is this criterion due to Harris that tells you when this should be true. It shouldn't be true for every Gaussian field. It should only be true if your correlations satisfy some decay condition. So you can translate this to basically decaying like power 3/2. But interestingly, and this is what Bogomolny and Schmidt observed, is that the Bessel function has this nice oscillation behavior, such that if you integrate it in this way, this double integral, you get massive cancellations that make it satisfy the Harris criteria. So even though naively you wouldn't think the random plane wave lied in the Bernoulli percolation universality class, due to the oscillations in the covariance, you get cancellations, and it suggests that it should. But this is very speculative, I should say. We don't really have a good handle on this, on making this Harris criterion rigorous at all. Okay, good. So yeah, I guess I have about 10-15 minutes left to try and explain some aspects of the proof. So let me proceed to that. So it's helpful to first recall, before comparing what we do in our proof, it's helpful to recall the classical approach due to Keston and then extended by Bolla-Riordan and Bafara-Monocopin to proving for any planar model that the self-dual point is critical. So there's a general strategy that's been used time and time again for all these different models. And the strategy goes as follows. So first of all, you look at the critical level, or the self-dual level. You look at the self-dual level, and you use self-duality to establish some properties of the self-dual level. So in particular, you prove so-called box crossing estimates. This is known as Russo-Simmer-Welsh theory in percolation. So you say that at the self-dual level, you can always cross rectangles with probability that's kind of controlled below and above. You have these kind of box crossing estimates. That's step one. And once you've proved this about the self-dual level, you use this as input into some differential inequality to show that around the self-dual points, you have a sharp phase transition for your box crosses. So you use, so the history is that Keston did this more or less by hand. Bolle-Riordan realized that there was a nice tool coming from theory of Boolean functions called BKKL, KKL inequality, and that's what they used. And then Dumenil-Copin, Bafara also used this, but more recently there's been work using a different inequality called OSSS to prove this phase transition. But anyway, yeah, the order of these things are clear. First of all, you study the self-dual level, and then you prove the sharp threshold using the differential inequality. And finally, once you have this sharp threshold, you can deduce that the self-dual point had to be the same as your critical point. That's the general strategy. So what we do is, yeah, we can't rely on this. Let me point out, we can't rely on this strategy because this first step really requires positive associations. In order to do this kind of Russo-Simmer-Welsh theory, you need these gluing constructions that I explained. You need to be able to glue rectangle crossings together to build larger ones, etc. And if you can't glue things together, you can't do this theory. So what we do is we reverse the order of the first two steps. That's really maybe the main insight into the main difference in our approach, is that we say, well, we don't know anything about the self-dual level, but nevertheless, we can prove the sharp threshold result without identifying where the threshold is. So that means that we look at rectangles on large scales and we say that there has to be some level around which the crossing probability concentrates, but that level may not be zero. It may be anything. It may be arbitrary. We can't identify it, but we can prove an abstract sharp threshold result. And then, yeah, but also there's another problem, is that we can't use the differential inequalities I mentioned because all of them also use, at least implicitly, positive associations. So we have to use a different technique. And what we use is a technique based on an idea of Chatterjee, which he calls superconcentration, which has some similarities to this BKKL that came before it, but it has some differences as well. And yeah, I'll try and mention more about that in a second. And once we've identified that all crossing events have sharp thresholds, although we don't know where the critical point is, what we do is we redo Russo-Simmer-Welsh theory without needing gluings by injecting the sharp threshold result into the theory. So we kind of avoid the need for gluings by first proving sharp thresholds and then redoing Russo-Simmer-Welsh theory. And the upshot of all of that is that you see that the self-dual point has to be critical. Okay, maybe it's a little bit hard to understand what I'm saying unless you're familiar with the percolation arguments, but I wanted to highlight that what we're doing is like reversing the order of this this argument, and that somehow yields this ability to bypass positive associations. And it's this high-level view of the proof that could be adapted to other models. I mean, here I'm not mentioning Gaussianity at all, and you could hope that you could follow this strategy to understand, say, yeah, other non-FKG models. So let me try, and I won't have time to discuss both steps. I guess I'll focus on step one. How do we use Gaussianity to prove this sharp threshold result? What is the role of Gaussianity? Okay, so what we say is we want to study, we want to fix a rectangle, and we want to understand, and we want to, okay, let me go a bit slower. Okay, so we want to consider, we want to fix a topological rectangle. So we call this a quad, but you can just think of a rectangle. So it's just a diffeomorphism of a rectangle in general. And we want to consider the event that if I look at a certain level and I look at the quad, whether or not the excursion set crosses the quad from left to right. So I fix the quad, and I'm going to vary the level, and I'm going to consider whether or not my crossing has occurred at a given level. And then we say, well, because this event is increasing, if for every realization of the field, there has to exist some level at which the crossing occurs, stops occurring. Sorry, it starts occurring. So if my level is too small, then clearly my excursion set is close to empty, and so it shouldn't cross the rectangle. But as I raise the level, I fill in more and more of my excursion set, and at some point, some random point, I do cross the rectangle. So to every quad, we can associate a random variable. It depends on the realization of the field, that tells me where the crossing happens. It tells me where the threshold is for that quad. Okay, that's what we call the threshold associated to the rectangle. Okay, and then we say that, well, because we're working with smooth functions, what happens at this threshold height is that the topology changes because you've passed through a saddle point. Okay, so if we look at this picture on the top, we see that the crossing occurs at a saddle point when I'm at the height of a saddle point that kind of has arms that connect me to the two sides of the rectangle. So associated to this change in topology is both a height at which it occurs and also a saddle point at which it occurs. So in fact, we have these two random quantities associated to our rectangle. That is the saddle points at which the topology changes and the height at which it changes, at which the crossing changes. Okay, and what this theory of superconcentration tells us is this very remarkable fact, is that we're interested in the concentration properties of the height. So remember, we want to say that roughly the probability of crossing changes rapidly from 0 to 1 as you push through this critical level. So in terms of the random variable t, the threshold height, that's really saying something about how concentrated it is as a random variable. We want to say that its law is very close to a delta mass at some level. Okay, and what our theorem says is that the concentration properties of the height is equivalent to the deconcentration, the delocalization properties of the saddle point. So if you knew that the threshold saddle point was kind of uniformly spread in its probability mass over your rectangle, that implies that the height is concentrated. You can think of it as some sort of Heisenberg uncertainty principle. Either you have localization of your saddle point, or you have localization of your height, but you can't have both. The delocalization of one implies the concentration of the other, and vice versa. It's not obvious at all why that should be true, but that's really what allows us to prove concentration of thresholds by flipping the emphasis onto delocalization of the saddle point. So this kind of idea is really due to Chatterjee. So his setting was different. So his setting was he wanted to understand how the maximum of a Gaussian vector concentrates. So it's well known that if you take a Gaussian vector, then the law of the maximum is very sharply concentrated around its mean. And that's true if and only if the location of the argmax of the vector is delocalized. So what Chatterjee was able to do is relate the delocalization of the argmax location to the concentration of the maximum of the vector. And what we do is we translate, or we reapply his ideas in this different setting to prove the same thing, except we're interested in concentration of crossing events and delocalization of saddle points. But it's the same, basically the same proof ideas and the same reason it's true. Okay, and we can make this precise. So maybe I'll skip this slide. It's just a quantitative version of this thing. It says that the variance of the threshold is small if you know something about the delocalization of the saddles. So why is this helpful? I should stop soon, but let me just finish on this slide maybe. So why is this helpful? Because it's hard to prove that the threshold height is concentrated, but it's sort of easy to prove that the threshold saddle delocalizes as the scale grows. So if you take a rectangle on very large scale, it's kind of easy to prove that you shouldn't have any subset of the rectangle at which you're very likely to see this key saddle point. The key saddle point should be spread more or less homogeneously around the rectangle. And to get that, we just need very, very soft properties of the random field. So yeah, Gaussianity was very important. So the only place Gaussianity appears in the proof is when we use Chatterjee's approach. So to prove this equivalence, we need Gaussianity. But once we've got this equivalence, Gaussianity goes away, and we just need to rely on soft properties like ergodicity and symmetry. So the facts we need is, well, if you want to prove that this saddle point shouldn't be localized in the bulk of the rectangle, what you're saying is that there shouldn't be any point in the rectangle where you have at this level at which the topology changes, you have your saddle point has arms that connect to infinity. So it shouldn't be true that if you look at a saddle point of the field and you look at the level sets at this height of the saddle point, you can think of those as arms leaving the saddle point, 4 arms. It shouldn't be true that those go very far with high probability. It should be that the probability of these arms connecting far decays at infinity. And in fact, that's true as soon as you have ergodicity. So that tells us that in the bulk of the rectangle, you can't have localization of your saddle point. So that's half of what we need. And then we need to consider the boundary of the rectangle. So we need to know that there's no, the saddle point's not localized somewhere on the boundary. And for that, you need to consider level lines in half spaces. If you're close to the boundary, then the rectangle looks locally like a half space. But by restricting to the half space, you again can prove that you have no unbounded level lines. So note that what we're trying to prove is on the plane, there's no unbounded level lines. On the half space, you do get that almost for free. I mean, it's not too hard to prove that on the half space, you can't have unbounded level lines. And this is just due to ergodicity again. Okay, and yeah, here we're using really classical ideas in percolation theory. Good, and so the upshot of this argument is that if you look at a fixed rectangle and you look at it on larger and larger scales, the variance of the height, the variance of the threshold at which the crossing changes goes to 0. So this is what I mean by we have concentration of thresholds, but we don't know where the mean of that thing is, because we didn't do step 1 of the argument. We didn't do the Russo-Sumo-Welsh, so we don't know where the mean of this thing is. All we know is we have concentration. And so then in the second part of the argument, we exploit this concentration to fix the mean to be 0. And once the mean is 0, then we know 0 is critical. Okay, yeah, I will skip the second part of the argument. And yeah, I guess I should stop there. So thank you.
Okay, thank you, Stephen. Yeah, very nice talk. Before we move to questions, you know, always there is some time for advertisement. So I would like to advertise next week's talk by Ross Mahler from ANU, Ross with us. So remember that next week we have seminar again. And now time for questions. Please just, if you have questions, ask Stephen.
Well, it's not a very deep one, but I guess the log-log comes because of the Gaussianity, is it? Some kind of log-log bound that you need.
Actually, yeah, I mean, it's a good thought, but actually it's not,
not right.
Where it comes. Well, actually, let me think about this. Yeah, so it comes from this. It comes from Chatterjee's superconcentration argument. So it comes from a sort of large deviations version of the argument. I mean, so what I said at the conclusion of this this step is that we know the variance is small, but actually what we need is something stronger than this. We need some large deviations for this threshold T. We need to know that yeah, beyond some scale, yeah, this thing decays very rapidly, and so it comes out of the large deviation estimates you can get for T. Whether or not ultimately it comes from the Gaussianity, yeah, probably it does, but not directly. Yeah, but we don't really, yeah. So we do need some quantitative. We don't think that there's any way to get purely a quantitative condition, and so we're not even sure whether or not this result is true in the level of generality that the physicists suggested should be true. I mean, we have this quantitative condition, so it would be very interesting to know whether or not in the generality of the physicists, it was true whenever you have qualitative decay. We're not 100% sure of that. There may be, you need some quantitative information, but we don't know for sure. We don't have any candidates for counterexamples even.
Hi, Stephen.
Yes.
What would you expect if you relax the smoothness assumption a little bit? If your Gaussian field is less smooth, then
yes. So okay. So C3 smoothness, it's clearly just convenience. But if you think about what we're doing in our argument based on saddles, so clearly we need some sort of Morse theory properties. I mean, we're saying that the topology changes if and only if you pass through a saddle point. Right. So this is, you need some sort of smoothness for this statement to be true. I mean, yeah, continuity is not going to be enough to tell you when the topology changes of your level sets. So there's no hope to use this kind of argument to understand rough fields, but certainly the conjecture, you can make the same conjecture for continuous stationary Gaussian fields. And yeah, but you need different techniques when you're working with rough fields. Yeah, you can't rely on these kind of topological considerations. But yeah, so the rough case is very, very interesting, and we would like to understand it better, but you do need different techniques.
Steven, somehow because probably it was too quick, I missed this part about half plane, but question is, so you have on all plane, you have this infinite component. What kind of figure can guarantee that you can have this infinite component, like angle, strip, or whatever, if you consider not all plane?
Yeah, so exactly. So first, to prove this in the half, so it's true that if you restrict to the half space, then purely using ergodicity and symmetry, you can rule out unbounded level lines. So you don't need Gaussianity here. So you're correct to say that first of all, you study strips, and you say that by ergodicity, there cannot be unbounded level lines in a strip. And then you extend it to quarter planes, and then you extend it to half spaces. Half planes, but you can't push beyond half planes.
But if you have something which is more than half plane, so some, okay, maybe
yeah, like three-quarter,
yeah, something like that, yeah.
Yeah, at least it's not clear. I mean, the technique used to prove this half space, it doesn't. You can't push beyond some. Yeah, there's some boundary at the half plane. For this to work. I guess it's probably true as soon as you restrict, say, a segment of the plane, it's probably true that any ergodic symmetric random field has no level lines that stay restricted to any, if you remove any angle of any segment. I think that's true. We don't know how to prove that. I don't think it's true on the plane. So you can come up with counterexamples on the plane where you have unbounded level lines. Even if your field is ergodic. So it's not true on the plane in complete generality. Yeah, but somehow removing a bit of the plane really helps you make these arguments, because you kind of exploit the symmetry and the ergodicity to force the line to really fill up the whole plane somehow. And yeah, and it's a bit like in percolation theory. So this key open question in percolation theory, that there's no unbounded connected components at the critical points in Z3. If you restrict to a half space, this is true. So this has been proved that if you have percolation on Z2 cross Z plus, there's no percolation at criticality. So it's the same idea. If you restrict to the half space, you can prove many things that you can't prove in the full space.
Okay.